suppose that we have two coherent sources. By coherent we mean that they're emitting waves in phase. And those waves come out in concentric spheres. So these spheres represent the positions of the wave fronts at equal time intervals. Okay? So the wave pulses, or these represent, let's say, the peaks of the wave at a given instant. Now, at the points indicated in red, a peak of the wave that comes from this source is meeting a peak of the wave that comes from this source. These peaks will reinforce each other. The waves will be in phase and will have a strong reinforcement of the peaks. So we'll have points where the waves are at maximum amplitude here. In between the peaks, we'll have a point like in between this peak and this peak. We'll have a point here where this wave is in its valley. So that the valley of the wave coming out from this source between these will be meeting the peak of this one, and everything will cancel out. So that we'll have regions of in phase and regions of out of phase, and those regions will be constant. Okay? It turns out that those regions form hyperbolas. So if we have the two forces here, the in phase regions will be hyperbolic, like so. Okay? Now, we can understand this. The two sources are coherent. They're emitting waves in phase, so that a peak leaves this one at the same time it leaves this one. They're going to travel the same distance to get to this line, so they're going to still be in phase when they get there. They're going to meet in phase. Okay? Now, it might be that along this line, the wave that's transmitted from here gets there ahead of the wave that's transmitted from here, but it gets there exactly one wavelength ahead. So that the path difference, the difference between the distance from here to here and here to here, is one wavelength. Okay, so we have the locus of points where the difference of the distance from this point and the distance from this point is always the same. That's the definition of a hyperbola if you remember your pre-calculus. Okay, along this, the path difference, we're two wavelengths closer to this source than this source. But that means that a peak is still going to meet a peak. The peak that comes from this wave will have been emitted 2 cycles earlier than the peak that comes from this wave, but we're still going to have peak meeting peak, because this wave travels exactly 2 wavelengths further than this one, so the peaks will still meet the peaks. Okay, that's just like over here. At this point, this wavelength, or this wave has traveled only 1 wavelength, whereas this one has traveled 1, 2, 3 wavelengths. So this one was emitted later than this one. This one came out earlier, but they still met peak to peak, because this distance is 2 wavelengths, exactly 2 wavelengths less than this distance. Now, if we have coherent monochromatic light, okay, that's coherent light, meaning it's all in phase, coming along like this, and it's all the same color, which means it's all the same wavelength, it turns out. So we have coherent monochromatic light coming into a barrier where there are 2 slits. What's going to happen is, remember, every point of the wavefront serves as a source for wavelets. So we're going to have wavelets coming out of here and wavelets coming out of here. Since this light is coherent and monochromatic, and implicitly we assume that the direction of propagation is perpendicular to this screen, then every peak that comes out of here will come out at the same time as the peak that comes out here. So we're going to have the same situation that we had before, where we have reinforcement and cancellation. Now, if we allow those peaks to move over to a screen, and let's pretend the screen is a lot further away than it looks. There's a little break here. The screen is way far away here. There will be a point in the middle where the distance here is the same as the distance here. Since these things were emitted in phase, they will have traveled the same distance, and they'll meet at the same phase. Now there will be a point here where this distance is 1 wavelength greater than this distance, so that a wavelet that reaches here will meet a wavelength that came from here one cycle earlier, because it traveled one wavelength further, but the peak that comes from here will still meet the peak that comes from here, because this one traveled exactly one wavelength further. Now in between there's a point where the one that comes from here traveled only half a wavelength further than this, and it'll therefore be at its valley when this one's at its peak, and they'll cancel out and give you a minimum. So that we have this configuration of minimum and maximum brightness of the light. Maximum where the peaks reinforce each other, minimum where the peaks meet the valleys, and the light pretty much cancels itself out. This happens well, let's go down here for a minute. Let's say that these are the two sources and these are rays of light coming out from the two sources. Theta is the angle at which the rays both go. Both of these are parallel rays, or pretty much parallel. They're going to converge at a distant screen, but the screen is so far compared to this distance that there's very little difference in these angles, so we're going to say that they're both essentially the same. Now we can draw a little triangle here. If d is the distance between the slits, then this angle, of course, is equal to this angle, because this is perpendicular to this, and this is perpendicular to this, so that the angles have to be the same. This distance here will be equal to the separation times the sine of this angle. So that d is, or the distance here is d sine theta. Now, from this point on, the two waves travel equal distances. The d sine theta is the extra distance that this wave travels. You see a picture here of this triangle with the slit separation d and the d sine theta difference here, the angle theta here. Now, d sine theta is the difference in the distances. When d sine theta is equal to a wavelength, as we've said, we get a maximum. Down here it can be equal to a wavelength. Down here it's equal to two wavelengths, and we get a maximum. Okay? When it's equal to 1/2 wavelength, we get a minimum. When it's 3/2 of a wavelength, we get a minimum. Because when it's a whole number of wavelengths, one wave will have traveled exactly, the peak from one wave will meet a previous peak from the other. Okay? Because the waves will have traveled exactly a whole number of wavelengths. The difference in the distance will be a whole number of wavelengths. It's getting late, sorry. Again, this is all based on the hypothesis that these two sources are in phase.